these are some practice problems for Newton's second law. They're all basically Atwood machine problems, so I'm going to do them all together in one video. It's going to be great. So let's just do a quick review of the main big ideas. Let me put that right here. So first of all, we have Newton's second law. It says this. I like to write it like this. The net force on an object is equal to its mass times acceleration. And so we can have a bunch of forces. Let's just put some 3, F1, F2, F3. So this says F1 plus F2 plus F3 equals mass times acceleration. Whatever that may be, that's fine. Now, how do you add vectors? Well, you add vectors by breaking them to components. So really, in most cases, it's going to be best to say this. F net x is F1x plus F2x plus F3x equals mass times acceleration in the x direction. So these are the components in the x and y directions, and we'll do. I'm not going to go over that. We'll do that in a little bit. And then also in the y, F net y is going to be the sum of the y ones, and it's going to be equal to mass times acceleration in the y. Now, trick. We can pick the direction of the x and y axis such that one of these is 0. And it's going to make our life much easier. This is really useful when you have like an inclined plane like that. If you have the block accelerating down the plane, then pick that as the x-axis, and that way the acceleration in the y direction is 0. It's not, you don't have to. It's not the rule. It's just a really good idea. And then other than that, we have a couple special forces. We have the gravitational force. Fg is mg. We have the normal force, which is perpendicular to the surface. It could be any value. We have the tension. Again, it can be any value, but it's only in the direction of the string. And then finally, we have the frictional force. We have two versions of this. So this is the static friction force. If the two objects are not moving relative to each other, then the frictional force is up to some coefficient times the normal force. And this is a magnitude because it's actually parallel to the surface, and that's perpendicular to the surface. If they're sliding, then we use a different coefficient. These depend on the types of materials. Let's get to it. Okay. First problem. I made these problems. And I know that the picture looks a little small. The words are small, but I'll tell you what it says. So we have an Atwood machine, and I didn't say it, but let's say that the pulley has 0 mass, 0 friction. So it's just these two masses connected by strings and one string. One's 1.2 kilograms, one's 1.9. And so the question says, what's the acceleration of the block? So I'm going to start off with a free body diagram for this one. I'm going to call this mass 1 and this mass 2. Now, I know that this one's going to accelerate down and that one's going to go up. They have to do the same thing if the string doesn't stretch. But let's draw M1. So here's mass 1. I have a downward gravitational force. I'll draw that as M1G, technically a vector. And then I have the tension going up. I'm going to draw it a little bit bigger because I know that if this is going to accelerate up, because that's the heavier one, then the tension has to be bigger. If you don't know that, it's cool, right? Because it's going to work out in the end. And so this is M1. And then M2 looks similar, except that it has a larger gravitational force, M2G. It actually has the same tension pulling up. Why are these tensions the same? Because it's the same string. This string goes over, and if there's no mass for the pulley, then those two have to be the same tension. If they weren't, then the string would do weird stuff. Okay. Or it'd have mass. So let's switch over to paper because I want to have more room. So I can write down Newton's second law for both of these masses. So for mass 1, I'm just going to write it in the y direction, right? Why not just do it in the y direction? For mass 1, I have tension in the positive y direction minus m1g, and that's going to be equal to mass times acceleration. And I said which way it was accelerating, up. So it's going to be m1a. So I'm picking y is up and x is that way, even though there's nothing in the x direction. And I don't know t and I don't know a, so I can't solve this. But this is m1. Let's do the same thing for m2. It looks very similar. F net y t minus m2g, and that's going to be equal to m2a, aha, negative, right? This one's accelerating in the negative direction. Now look at what we have. I have two equations and two variables. I don't know t, I don't know a. I don't know t, I don't know a. So we can solve two equations, two unknowns. Now, it is possible to subtract or add equations, and that's often a good trick. I'm not going to do that because there's cases where it doesn't really work, so I'd rather just solve. Let's solve this for t and substitute that in here. So I'm going to solve this for t. Solve for t. T, I'm going to add m1g to both sides. I get m1a plus m1g. Now I'm going to substitute that in up here. Sub. So if I put in t, I put this expression, I get m1a plus m1g minus m2g equals negative m2a. So all I did was, instead of t, I put that. Now I want to solve for a. So let's just, I want to add this to both sides and then subtract that. So I get m1a plus m2a, and then subtract that from both sides. That's an a. It's going to be, and subtract that, m2g minus m1g. And I can factor out the a, m1 plus m2 equals g times m2 minus m1. And then I'm going to divide both sides by m1 plus m2. And I get a is g m2 minus m1 over m1 plus m2. Now, we're going to plug in our values because I have values. But I'm not going to yet because I want to make sure a couple things. Does this have the right units? So the units for the mass up here, mass plus mass, is going to be kilograms. And the same thing's down here. So I have kilograms over kilograms. And so kilograms divided by kilograms is just no unit. And then G has units. G is, the magnitude of G is 9.8 newtons per kilogram, which is the same as 9.8 meters per second squared. Since a newton is it's a kilogram meter per second squared. So that's going to have units of acceleration, so that will too. Now let's look at the a couple special cases. So suppose that these two masses were the same, both 1.9 kilograms. What would the acceleration be? I think you can figure that out in your head. It's going to be balanced. They're not going to move. Acceleration 0. So if m1 is equal to m2, I should get 0. If m1 minus m1, I'd get 0. That works. What if this mass is ginormous compared to that? What if m2 is much greater? And so if that case, this would basically be m2 on the top, and this would be basically m2 on the bottom, and I'd get g in the negative direction. So that makes sense too. I did free fall acceleration. Okay, so it looks like it's working. Let's put in our numbers just to make everyone happy. So I'm going to say clear. This is good practice with your calculator. I like to put it where you can see it. So I can put 9.8 times parentheses 1.9 minus 1.2, which I could have done that in my head, but you know, it's 0.7. Divided by parentheses 1.2 plus 1.9 close parentheses equal. And I get 2.21 meters per second squared, which is less than 9.8, which is good, right? It wouldn't accelerate faster than 9.8, and it's greater than 0. Now, I did go through that fast, but that's because I'm going to do another problem. I want to fit them all in, and you're going to get more practice. So, you know, don't feel like you have to just zoom through this. Things make sense when someone else does them. It's not until you do them that you get stuck that you really understand it. So actually, let me explain this problem, and then you can pause the video and try to figure it out, and then come back. This is called a half Atwood machine. So it actually has the same two blocks, but now one of them's on a table and the other one's hanging down. So what's the acceleration of the blocks? And there's no friction. So let's draw a free body diagram again. Let me draw the thing. So here's M2, M1. So let's draw two free body diagrams first for that one. So here's my box. I have the gravitational force, M2G. That's the only long-range force. Other than that, I have things that are touching it, which are the table pushing up, N, and the tension in the string this way, T. The block is going to accelerate that way, right? It's not going to go up or down. So it makes sense to call this the x-axis and that the y-axis. And so we can go ahead and write the Newton's second law for this object. F net x is going to be equal to t, and that's m2a. That's the only force in the x direction is t, and it's going to accelerate that. So I don't know t and I don't know a. So again, we're in that same position. Now let's do the other block. Here's m1. This is going to have the downward gravitational force, m2g, and then the upward tension force, which has a different direction, but the same magnitude because it's the same force. It's the same string. And I'm going to say, the other thing that's important to realize is that if this is accelerating that way, I picked it to accelerate this way, this is going to accelerate down, right? Because the string has to stay the same length. So let's write the net force in the y direction for this one is going to be t minus m1g, and that's going to be equal to minus m1a because I said it has to accelerate down. But again, I have two equations to unknowns, so I can solve. I already have this one solve for t, so I'll just plug it in down here. I get m2 minus m1g, m2, I was too excited. So I get m2a minus m1g equals negative m1a. And I'm going to add this to both sides, subtract that from both sides, or add that to both sides. I get m2a plus m1a equals m1g. Factor out the a, m1 plus m2 equals m1g. And then I'm going to divide both sides by m1. A, m1g over m1 plus m2. I didn't point this out in the last problem, but it's two equations to unknowns. If I find the acceleration, I can always go back and find the tension if I want that. I didn't ask for that in this problem, so I'm not going to solve for it. But now let's check the units again. So up here I have mass times meters per second squared divided by mass, which gives me meters per second squared. So the units work. Let's check out the extreme cases. If m1 is super, 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 super tiny, then this shouldn't have an acceleration. It should just sit there, or it should be very close to zero. So if m1 is very, very small and divided by something that's much bigger, m2 plus m1, then a would be very close to zero. The other way around, if m1 is giant and m2 is very small, it should just be like free fall. So if I have m1g and then I divide by something that's almost m1, I get g. So that does seem to work. Let's put in our numbers. So I had m1 was 1.2. Okay, the smaller mass. So I'm going to put that. So clear. So 1.2 times 9.8 divided by parentheses 1.2 plus 1.9 close parentheses, and I get 3.79 meters per second squared. And I've already taken into account the direction when I set up the problem. I already said that one's accelerating that way and that one's accelerating that way. So that's just the magnitude. There you go. That one's actually easier than the real Atwood machine. Next one. I think there's 4. Yeah, and this one, the next two get a little bit more challenging. This is the same problem, except that. In this case, there's a frictional force on this one. with a coefficient of kinetic friction of 0.12. So we already have the free body diagrams. In fact, I could go over here. This is the previous problem. What's going to change here? Well, if it's still accelerating that way, then there's going to be a friction force parallel to the surface. I'll call it FF, and pointing in the opposite direction of the sliding motion. And that has to be less than the tension or it won't move. So this equation is going to change. Let's just rewrite these because I don't want to contaminate that. So this equation in the x direction now is going to be T minus the friction force equals m2a. But I don't know the friction force, right? So now I actually need to look at also the y direction here. So I can say F net y is going to be equal to n minus m2g equals 0. This one does not accelerate in the y direction. So it has an acceleration of 0. So that means I can solve for n as equal to m2g. Be very careful. A lot of people just say, oh, the normal force is the weight. The normal force is not always the weight. Only it happens to be a lot that it is, but it's not always true. Now that I know the normal force, I can find the kinetic friction force. F friction is going to be equal to mu k, which I know, times the normal force, which is mu k times m2g. So if I put that in up here, I get T minus mu k m2g equals m2a. Now, back to this other problem. The hanging mass is the same. There's no difference. There's no friction there. So I can just write down the same equation. T minus m1g equals negative m1a. Yep. So I again have two equations, two unknowns. It's just that they're not as nice. So which one do you want to solve for first? Let's solve for t. It doesn't really matter which one. I'll solve this one for t. So if I solve for t, why am I writing solve for t? Then I get t equals m1g minus m1a, right? I just add m1g to both sides, and I get that. Now I can substitute that in up here. I get t, which is this, m1g minus m1a, minus, now I have the rest of the stuff, mu k m2g equals m2a. Now, there's only one thing I don't know. I don't know a, and I don't know a. So I want to get those two on one side of the equation. I'm going to add m1a to both sides. So I get m1g minus mu k m2g equals m1a plus m2a. I'm going to factor out the a, so it's going to be a m1 plus m2. Now I can divide both sides by this m1 plus m2, and I get a equals m1g minus mu k m2g, all of that over m1 plus m2. Let's check the units. So here I have mass, mass, mass. All the masses cancel, so that I don't have to worry about the mass. Meters per second squared, meters per second squared. Mu is a coefficient. It doesn't have units. So I do get meters per second squared. Now, what about the case where the coefficient of friction is 0? Then it should be the same solution that we got before. So if I put in mu k as 0, I get m1g over m1 plus m2. That's what we had before. So other than that, everything should work out fine, right? And the greater this coefficient of friction, the lower the acceleration. And remember, mu k I had was 1.2. Is that what I had? Yeah, 0.12. Now, it is possible that you could get a number here that would have a negative acceleration. If that's the case, bad things happen, right? Because you already assumed the direction. Getting a negative acceleration means that it just wouldn't move. But I think I worked out the numbers fine. So let's do these numbers. Can you see that right there? Okay. Clear. So I'm going to put, I have two numbers on the top, so I need to put parentheses to begin with. M1 was 1.2. Yeah. 1.2 times 9.8 times, oops, clear, parentheses, 1.2 times 9.8 minus 0.12 times 1.9 times 9.8. And you really, when you're entering in your calculator like that, you gotta change the level of your voice, or it won't be interesting and not fun. Divided by, see, parentheses, 1.2 plus 1.9 close parentheses equals, and I get 3.07 meters per second squared. And let's just check, right? We did this before. I got 3.79. So with friction, the acceleration is going to be lower. That makes sense. Okay. I know I've been going fast. You got to pause. Just pause when you need to pause. I'm going to assume that you pause. Last problem. I actually have one more, but I'll make it a separate video. This is the inclined half Atwood machine. 25-degree angle. No friction. You can do this with friction, but it gets a little complicated. So what's the acceleration? This one, now we're having fun. So let's go ahead and write our two, let me draw it on here. Let's draw our free body diagrams on here. So this mass is going to have a gravitational force, m2g, tension, T, normal force, N. And this one's going to have, just same as before, M1G, tension. So the trick here is that this block is going to accelerate that way. And so it's actually okay to have a coordinate system for this one that's different than that one. And that's what we're going to do. I'm going to pick this as the X direction and this as the Y direction. And because if I do that, then I know the acceleration in the Y is 0. It's going to make my life much easier. So let's look at mass 2. Let's write down my two equations, even though we don't actually need them both. So let's say mass 2, I have in the Y direction, F net Y is going to be N minus this component of the gravitational force. The gravitational force is not all in the Y direction. So if I look at this little triangle here, I'm looking at the adjacent side. This angle is 25 degrees if that angle is 25 degrees. So we're going to look at the cosine. I'm going to just call it theta, and then we'll put in theta later. So I'm going to say minus mg cosine theta. Cosine, because my angles, I'm looking at the adjacent side, and that's equal to 0. Now, I could take this and solve for the normal force, because I know everything else, but I just don't care. So we're not going to. F net x. Now in the x direction, I have the tension pulling in the x direction. And I have this component of the gravitational force. That's the opposite side of that triangle. So we're going to use sine, and it's in the negative direction. Negative mg sine theta. And that's going to equal m2. That was m2, right? I called that m2. m2a. Now, I don't know t. I don't know a. Now we can look at m1. M1, it has the same diagram it has before. So I can just say F net in the y direction is going to be equal to t minus m1g. And that's going to equal negative m1a because it's accelerating in the negative y direction. But two equations, two unknowns. Let's solve this one for t. I get t equals m1g minus m1a. That's an a. Now I can substitute that in up here. I get m1g minus m1a. That's at t, right? Minus mg sine theta equals m2a. And again, I want to get all the a's together, so I'm going to add m1a to both sides. I get m1g minus, oh, that's m2. m2g sine theta equals m1a plus m2a, which is a m1 plus m2. And now I can divide both sides by m1 plus m2, and I get A equals m1g minus m2g sine of theta over m1 plus m2. Now again, we have a check, right? I could check the units. Masses cancel. Meters per second squared, meters per second squared. Sine theta's a ratio, it doesn't have any units as a theta. But what if, how do I get this back to this? Well, one way I could do that is to say this is theta equals 0. So if you put theta equals 0, you get sine of 0 is 0. So I get m1g over m1 plus m2, which is the same thing that I got before with no friction. So that tells me that I'm in the right direction at least. Let's go ahead and put in our values and see what this acceleration is. M1 is parentheses 1.2 times 9.8 minus 1.9 times 9.8 times sine of 25, that was my angle, close parentheses for the sine, close parentheses for the top, divided by 1.2 plus, well, I'm surprised I haven't made a calculator error because I'm not really good with calculators, 1.26 meters per second squared. And that's the acceleration up the incline and the acceleration down for the other one, which is less than the other cases. Now, if you're a physics instructor, teacher, faculty, whatever, and you're making physics problems, this is the problem. I'm just telling you because I've made this mistake. If you want a inclined half Atwood machine, work out the problem beforehand. Okay. It is possible that you could have it going down here, and that's not too bad because in this case, if I got an acceleration of negative, it just means I picked wrong, and that's fine. That means that I picked this going down, and that's actually going up, and this is going that way. Now, in the case of the friction, though, that doesn't work, right? Because if I get a negative acceleration for this, it means it's going up, and that one's going that way. But that's not the way friction works. It wouldn't do that. But the math that we use doesn't know that that's how friction works. So, okay, 4 Atwood machine problems, all dealing with Newton's second law. Again, I flew through that. I did 27 minutes for 4 problems. Take your time. Get stuck. Don't just look at it. Even if you watch it, go back and redo the problem. See how far you can get without watching it. When you get stuck again, go back and watch it. You're not going to learn this stuff by just watching a video, no matter how awesome my videos are. So I'm going to say that. Okay, that's that. I'm going to post some more practice problems. I have another one that's pretty good. I'll post that later.